In this video, we introduce the idea of implicit differentiation through a series of 3 examples. So in our first example, we're looking at the unit circle, and that's defined by the familiar equation x squared plus y squared equals 1. So that's a circle of radius 1 centered at the origin. And what we're trying to find here is the slope of the tangent line at the point 1/2 comma root 3 over 2. And then we're going to plot that tangent line in our plotting software just to verify that it works. Now, to give a little preview of what I mean by implicit differentiation, I want to look at this expression, which is just kind of a small part of what we have to accomplish here. What happens if I take the x derivative of a function of y? Well, it's important to remember that we're talking about points on an implicit curve and that y depends on x. So we have some unknown function of x squared, and we're trying to take the x derivative of that. We already have a tool to handle exactly this case, and that tool is called the chain rule. So what I'm looking at here is really a function composition. And to get the derivative, I take the derivative of y squared with respect to y. That gives me a 2y. And then I have to multiply by the derivative of y with respect to x. And again, that's simply applying the chain rule to some unknown function of x that we called y. So that's actually an example of implicit differentiation, and the thing that popped out of that we're interested in is actually the dy dx. So this is one of several cases in Calculus 1 where we've just given a new name to an old thing. Really, implicit differentiation is simply the chain rule. So let's see how to apply this to actually answer the question. Based on our experience differentiating y squared in general there, we know it's going to produce a factor of dy dx, in other words, the derivative, and that's the thing we're trying to solve for. So what I'm going to do is start with the original equation of the circle and then differentiate both sides with respect to x. Now when I apply that to the x squared, that just gives me a 2x. When I apply it to the y squared, remember y is some unknown function of x. So I start by differentiating with respect to y. This is what the chain rule says. And then I differentiate that interior function with respect to x. On the right-hand side, I simply have a 0 because the derivative of a constant vanishes. So we can divide a 2 out of this thing and then subtract x and divide by y, and we get dy dx equals negative x over y. So by using implicit differentiation, we were able to write down the slope of this curve as a function of 2 variables. Now, if we plug in an x and a y into that expression, we'll immediately get the slope of the curve. So we happen to be interested in a particular point. That's when x is 1/2 and y is root 3 over 2. And we can notate that by saying dy dx vertical bar and then the ordered pair that we're evaluating this at. All that means is replace x with 1/2, replace the y with a root 3 over 2. And if I clean that up by multiplying the top and bottom by 2, I get negative 1 over root 3. Now there's really no compelling reason to rationalize that. I'm just going to leave it as a negative 1 over root 3. And that's the slope of the tangent line at the point we're interested in. So now I still want to find the equation of that tangent line, and we're going to use the point slope formula for this. So I have y minus the known y coordinate. Y minus root 3 over 2 is equal to the slope, that's negative 1 over root 3, times x minus the known x coordinate, which was 1/2. Then I can add root 3 over 2 to both sides. And that's a good enough form for our tangent line. So I get y equals negative 1 over root 3 times the quantity x minus 1/2 plus square root 3 over 2. And this is the moment of truth where we plug into our plotting software to see if it actually looks like a tangent line. And so yeah, it works out. When we plot this thing, it's clearly a tangent line. It's touching the circle at exactly 1 point, and we're done with the problem. Now our next question has a little different flavor to it. This time the equation of our curve is x squared minus xy plus y squared equals 4. That turns out to be a rotated ellipse. And what we're asked for is to find all the values of x for which this curve has a horizontal tangent line. So I've already shown them in the picture. x1 is the negative value of x corresponding to a horizontal tangent, and x2 is a positive value of x corresponding to a horizontal tangent. And to answer the question, we just need to get an expression for dy dx, and then we're going to find out where that's equal to 0. So again, we have a little bit of experience differentiating functions of y with respect to x. And we know what happens there is that the chain rule produces a factor of dy dx, and that's what we're interested in. Just keep in mind as you go through taking these derivatives that y is some unknown function of x, and that you have to use the chain rule. So in our first term, we just get the x derivative of x squared, which is 2x, no big deal. The second term is a little more complicated because that's a product of two functions. So I need to use the product rule for this, and in the first term, I take the derivative of x multiplied by y left alone. So I end up with just a negative y coming out of this. And in our second term, I leave the x alone and I differentiate y with respect to x. Well, that's just dy dx. And then in the last term, we differentiate y squared with respect to x. Again, we take the derivative with respect to y, that's 2y, and then we multiply by the derivative of y with respect to x. On the right-hand side, we have a 0 again because that was a constant over there. And then I start working on solving for dy dx. So I have two terms in here that don't have a dy dx in them. I'm going to move those to the other side. So I add y to both sides and I subtract 2x and I end up with a y minus 2x on the right-hand side. Now on the left-hand side, I can factor out a dy dx, which is the thing I'm trying to solve for here. And when I factor that out, just reversing the order here so it looks a little nicer, I'm left with a 2y minus x. And now I can solve for dy dx. So now in principle, we can take any xy pair on this ellipse and plug it into that expression, y minus 2x over 2y minus x, and we'll get the corresponding slope of that point on the curve. What we're interested in particular in this example though, is all the points where the slope is equal to 0. Well, that only happens in this fraction if the numerator is equal to 0. So looking for the points where the slope is 0 is the same as saying y minus 2x equals 0, which is the same as saying y equals 2x. So that's a condition that gives us a 0 slope on this curve, but we still have to find the actual x values where this occurs. So the key to the problem is to plug that constraint back into the original equation for the curve. Plug in y equals 2x and then find out what the values of x are where this occurs. So when I plug back into the curve, I get x squared minus x times y, but y is 2x, so that's minus 2x squared. Then my third term is a y squared, but y is 2x again, so that's 4x squared, and this is equal to 4. Now on the left-hand side, that gives me 3x squared, so I have 3x squared is equal to 4, so now I'm going to divide by 3 and square root the result, and I find that x is equal to plus or minus the square root of 4/3. Now, if I had written this question so that you had to find the equation of each of these tangent lines, well, you know the slope is 0, which makes those equations very simple. It's just y is equal to a constant. But you would have to take these x values and plug them into the equation for the curve to find the corresponding y values. But the way I wrote the question, I simply wanted the x values corresponding to horizontal tangents, and that turns out to be plus or minus square root 4 over 3. Notice that that number is slightly bigger than 1. And when I look in the graph, I see x values with a magnitude slightly bigger than 1. So that's encouraging. Now in our last example, we're not actually going to do anything with the graph of this function. I just thought it was a really beautiful graph, so I just included it just so you could see it. The curve we're looking at is 2y sine of xy equals y squared minus 2. And this time, all we're asked for is a general expression for the derivative dy dx. And aside from the pretty picture, the main reason that I included this example is because the algebra starts to get a lot more intense. So as you can probably guess, the strategy here is to take the x derivative on the left and right hand side. And on the left hand side, that's a product of two functions. So I'm going to view it as the product of 2y and sine xy. So I apply the product rule to this and I differentiate the first function with respect to x. That gives me 2 dy dx. And we leave the second function alone for this first term. And then in the second term, I leave the first function alone, which was a 2y, and then I tack on the derivative of sine xy. Well, that's a function composition, so I have to start by differentiating with respect to its argument. That just gives me cosine xy. You just treat the argument like a single variable for that first step. But then I have to tack on the derivative of xy, and that's a product. So the first term that results from that is going to be a 1 times y. That's the derivative of x times y left alone. And the second term is an x multiplied by the derivative of y with respect to x. That's dy dx. Now on the right-hand side, the minus 2 doesn't do anything there, but I have a derivative of y squared again, so that's 2y dy dx. Okay, now the goal is to get all the dy dx's on one side of this equation, and then we're going to factor it out. So what I'm going to do in this step is gather all the dy dx containing terms on the left-hand side. So there's that first term just left alone. And then we get another dy dx containing term when we distribute this 2y xy into these parentheses. The second term we get there has a dy dx in it. So I need 2y times x dy dx cosine xy. So 2yx dy dx cosine of xy. Now the other term we get there doesn't have a dy dx in it, and I'm going to go ahead and subtract that to move it over to the other side. Before I write that term, I want to take this guy, the 2y dy dx, and move it to the left-hand side. So I have a negative 2y dy dx. And then on the right-hand side, again, I'm subtracting the term produced by distributing into the first term of those parentheses. That gives me a negative 2y squared cosine of xy. So now we factor out the dy dx out of the left-hand side. I'm going to go ahead and write the second term as a 2xy. It's just more comfortable that way because it's alphabetical order. All right, so the dy dx is pulled out. And again, on the right-hand side, we still have a negative 2y squared cosine of xy. So now we're ready to state our final answer. We solve for dy dx by dividing by this huge expression that's stuck to it. So in the numerator, I have a negative 2y squared cosine of xy. And in the denominator, well, we divided by this entire huge expression that was stuck to dy dx on the left-hand side. So that's a 2 sine xy plus 2xy cosine xy minus 2y. So now if you're given an ordered pair on this crazy looking curve, you can just sub those x and y values into that expression and you'll immediately have the slope of a tangent line at that point. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left. Or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.